In this video, we'll look at the most efficient heat engine possible, which is called a Carnot engine. It follows what is called the Carnot cycle. So a Carnot cycle, we've seen isotherms before. So this isotherm, this is all at one temperature. This is a hot temperature isotherm. Then a cooler temperature isotherm is down here. Okay? So the heat engine follows this path once, and then it follows this path coming back, and in between it follows what's called an adiabat. Remember, an isothermal process, which follows an isotherm. There's no change in the temperature of the gas. An adiabatic process, which follows an adiabat on a PV plot, is a process in which there's no heat exchanged. Okay, so no change in heat here, no change in temperature, no change in heat, no change in temperature. So when you go through this process, you do some amount of work related to this blue area inside. Remember, the area inside the curve of a closed loop on a PV plot is the amount of work done. So in order to do that, we have to use an isothermal process and an adiabatic process. If we look at an adiabatic process, that means there's no heat exchanged. So you could do an adiabatic process by using insulation. Put insulation around the container that you're using. So insulation would work. Also, if you just go really fast, then there's no time for the heat to exchange with the outside world. So you can either insulate or you can go fast. Isothermal process, if I do something very slowly, then there's plenty of time for thermal equilibrium to occur between what's inside my container and what's outside. So if I go slowly, that could be an isothermal process. Go quickly, probably should have said quickly instead of fast, that's an adiabatic process. An isobaric process, this is constant pressure. One way to have an isobaric process is to incorporate some kind of a piston that if the pressure inside goes up, the piston will push out to keep it the same as the atmospheric pressure outside. If something happens to try to make the pressure go down inside, the piston will just slide in to keep the pressure constant. So using a piston open to the atmosphere is one way to keep an isobaric process. Isochoric process, that keeps the volume the same. Well, make a rigid container. If I force my container to always be the same size and same shape, then it could build up huge pressure differences between the inside and outside, but it will stay the same volume. For a Carnot cycle, you could just go slowly and go quickly, going back and forth between following the isotherms and the adiabats. Now, if you go through one cycle of this, the amount of work you do is related to this shaded area inside. How could you increase the amount of work done in one cycle? What you'd want to do is spread out the difference between the top and bottom, because that would make the area inside bigger. That means making the cold side colder or the hot side hotter. So as you increase the temperature of the hot side, you can do more work if you keep the cold the same. Or if you decrease the cold, you can keep the hot side the same and do more work per cycle. Looking at the equation for maximum efficiency of a heat engine, that was this one. We just said if you want the efficiency, the maximum possible efficiency, to go up, then you could increase the hot side. Right? If I make TH bigger, then TC over TH gets smaller. I'm subtracting something smaller, so this will go up if this goes up. If TC goes down, then this fraction, this goes down, and I'm subtracting a smaller number. So again, this will go up. So that's what's meant by this equation. Remember, this is only true for a perfect Carnot engine.